Hello everyone, this is Qingzhe from UT Austin. I'm going to talk about our work. The title is SPAMeR, Speculative Push for Anticipated Message Requests in Multi-Core Systems. This is a collaboration with ARM. Here comes the outline for my presentation. First, I will show what's the problem that SPAMeR is trying to solve. Then I will present the SPAMeR architecture from hardware, ISA, library, and algorithm perspectives. I will go through the evaluation of SPAMeR before concluding my presentation. Now, let's get into the motivation section. In parallel computing, some applications will make use of task-level parallelism. For example, the diagram here shows an example of network packet processing. While tasks like calculating checksum, verifying whether the source of the packet is whitelist or not, and payload decryption, all those computation tasks could just go in parallel. The upstream tasks and the downstream tasks are pipelined via message queues. Some of the message queue implementations, especially those hardware queues, could have buffers in multiple places. The producer might put the messages into its local buffer first. Then, at some time point, move the messages in a batch to where they will be consumed. This is usually done in an on-demand manner, that the consumer issues a message request when it is ready to accept a new message, and waits for the message to arrive. Despite of the simplicity, this on-demand approach would include allowed to use latency on the critical path, as shown in the figure. So the idea of the SPAMeR is really straightforward. How about we move the messages earlier without waiting for a consumer request in order to deliver the message right at the time when they are needed? In this way, we can now overlap the load to use latency under the computing time and also eliminate those requesting traffic. Move on. We are going to take a closer look at how SPAMeR implements this idea. We build SPAMeR atop of a state-of-the-art hardware queue called a virtual link, with some minor changes highlighted in red. How virtual link works is it has a routing device attached to the coherence network. And producer threads and consumer threads would have cache lines of different addresses as their local buffers. Once the local buffer is full, producer writes back to the routing device, and the consumer requests the routing device to get the data. SPAMeR replaces the consumer request and receive data, which are the marker 4 and 5 in the figure, with a speculative push issued from the routing device. In the routing device, a structure called a specbuf is responsible to keep the information for SPAMeR to make speculation decisions. Now, zoom into the routing device. Here, entries with different colors are for different queues. The bottom part of the diagram on gray background shows the virtual link routing device in brief. And we will also find SPAMeR routing device also makes a new path to look up the spec buffer. The new path goes in parallel to the existing virtual link address mapping pipeline. A multiplexer in stage 3 might choose a speculation target from the spec buff when no matching consumer request is found in the consumer buffer. Once a speculation target is taken by the address mapping pipeline, the message is logically added into a speculative push queue and will be sent out after some delay. The message could also end up with two other possible results of the address mapping. If there's consumer request found, the message is sent out as soon as possible. Otherwise, if neither consumer request nor speculation target are available, then we buffer the message for now. Depending on whether the message is filled into the consumer cache line successfully or not, the message might enter the address mapping pipeline again. This retry mechanism has been established in virtual link architecture already. So the only new thing added by SPAMeR is just the speculative push path. SPAMeR adds a new instruction called SPAMeR register to register a speculation target address at the spec buff. This new instruction works the same as the VL fetch instruction that virtual link uses to send a consumer request. The only difference will be SPAMeR register goes to send the consumer cache line address information into spec buff instead of the consumer buffer. The registration using the SPAMeR register instruction happens only once at the beginning of a program when the endpoint is created by the library. After that, the pop library function could now skip the requesting part of the code to save some time for consumers. We also apply function inlining on the most frequently invoked push pop functions. The last but very important part of SPAMeR design is the prediction algorithm. The first algorithm, we name it as zero delay, apparently because zero delay algorithm never add any delay to speculative push. Therefore, zero delay algorithm can always hit the very first chance to fill in a consumer cache line and save the latency the most. However, the drawback is the zero delay algorithm could make too many failed pushes. So the second algorithm, adapt, is proposed to reduce the number of failed speculative pushes. If a speculative push fails, adapt algorithm takes this as a sign of pushing too fast, so the delay is doubled. A speculative push hit would otherwise reduce the delay. This algorithm is very simple for hardware to implement, as shown in the diagram. And the pseudocode of the algorithm is also shown on the right. The adapt algorithm can effectively learn the pace, how fast the consumers accept the message for most of the workloads, while it is limited and fails to model some tricky situations. Therefore, we improve the adapt algorithm to adjust the delay with varying granularity. First, we calculate a reference interval from the most recent push history and set thresholds around the reference. When fall outside the threshold, we will adjust the delay in a multiplicative way, just like the adapt algorithm. But if it is closer to the reference, we gradually increase the delay with a fixed step delta. there are some design parameters in this algorithm, such as the thresholds and the step delta. So we call it a tuned algorithm. Now I'm going to show the evaluation results. We have a set of diverse benchmarks with different type of queues. Some multi-producer to multi-consumer queues, some single producer or single consumer. And the number of queues in each benchmarks varies too. The experiments are conducted in a well-known four-system simulator, GIM5. And the system configuration is in the table on the right-hand side. Here we say SPAMeR with the zero delay algorithm achieves great speed up on some benchmarks. And it has 1.45 times faster on average over the baseline virtual link. The tuned algorithm matched to the zero delay algorithm closely on most benchmarks and achieves 1.33 times speed up on average. We show a time breakdown here. The top part of the bars are for the cycles when consumer cache lines are empty, and the bottom part is for non-empty cache cycles. We can see for those benchmarks that the SPAMeR gets good time reduction. The time saved are mainly on those empty cycles. That is kind of expected, right? Because SPAMeR fills the empty consumer cache lines earlier, so it is those empty cycles got shortened. Here we show the speculation failure rate along with bus utilization. The zero delay algorithm obviously takes the failure rate way too high, and the adapt algorithm managed to control the failure rate within 50%. Remember, earlier I showed the speculation versus on-demand diagram. Because the speculation does not have the requesting traffic, the failure rate lower than 50% means there is a chance to have fewer transactions going on to the bus. And the bottom chart backs up this claim. We say SPAMeR with the adapt algorithm and the tune algorithm have a comparable bus utilization to the baseline virtual link. Lastly, we did a sensitivity study for the tuned algorithm. Each blue dot in the figure stands for a unique combination of the parameters. The parameters are those like thresholds and step delta. As we can see, the parameter choosing has considerable impact on FRR's speed and energy consumption. And the set of parameters we used all through the other experiments is the red cross, and it is on the side closer to the original point, meaning it is the optimal one we found. Other benchmarks are not very sensitive to the benchmarks parameters. I put the firewall as example here, and you can find the figures for other benchmarks in our paper. In summary, we show that massive queues with distributed buffer might waste the time on load to use latency. So we propose SPAMeR speculation mechanism as a solution to hide the load to use latency. And it show this design is able to improve the performance on top of a state-of-the-art massive queue architecture. Thank you for listening. Please let me know if you have any question.